So, or actually just improper limits are what we were dealing with, right? So we had all these indeterminate forms. And I wanted to remind you of those indeterminate forms. So here, let me share this so that it will be up on the screen, okay? So these were the indeterminate forms that we came up with on the whole, okay? 0 times infinity, infinity minus infinity, 0 to the 0, infinity to the 0, 1 to the 0. But of course, what were the two big forms that aren't listed here that in fact L'Hopital's rule is designed to handle? Yeah, that's right. So it was 0 over 0, right? 0 over 0 and infinity over infinity. Of course, there are pluses and minuses included here, right? So these could be plus or minus infinity over infinity, okay? We won't write that for 0 over 0 though, okay? We saw like these guys right here, 0 to the 0, infinity to the 0, 1 to the infinity. All of those can be tweaked into one of the other forms by taking logarithms and kind of undoing them with exponentials, okay? The 0 to the 0 is a little bit trickier. You might have to do something slightly trickier than that. But it turns out that taking logarithms, getting the power to come down is at least a step in the right direction, okay? Infinity minus infinity. Oh, and by the way, 0 times infinity, it's easy to manipulate that into L'Hopital rule form because you basically take the 0 thing and or the infinity thing and flip it into the denominator and it will become one of the forms that L'Hopital deals with. Infinity minus infinity, typically what you have to do there is factor out something and it will turn into the 0 times infinity situation. Does that make sense? Factor something out and typically it will turn into one of the forms you can turn into L'Hopital's rule. Okay, but L'Hopital's rule only deals with these two. So please only apply it in those cases, okay? Any questions on that? Questions? All right, so let's actually start discussing how we can apply this in an integral context, okay? So improper integrals is the last section of chapter 8, okay? So improper integrals, the last section of chapter 8. The last thing that you will be responsible for a week from today and on the test, yeah? Okay? So we have a week from today, we will have a test over chapter 8. Improper integrals will be the last thing that you're responsible for, okay? Now, basically what we're dealing with here are integrals that are improper, right? Because after all, the section is called improper integrals. Now, there are two ways that the integrals can be improper, okay? One way is that you can have infinite limits of integration, okay? The limits themselves could be plus or minus infinity. And you say to yourself, what on earth do we do in such a situation, okay? Or you could have a point in the interval. So now we're talking about definite integrals. Definite integrals are ones where you have endpoints that you're thinking about plugging in. Does that make sense? So far, we've been dealing almost exclusively with indefinite integrals. How do we find these antiderivatives, right? But now we're moving back into the realm of definite integrals. But the issue is we're going to have some badly behaved limits of integration. Either the endpoints will be infinite, or in the second case, you might have a point where you have discontinuity happening, or some kind of undefined situation happening in the interval itself. So those are the two types of situations we're going to deal with, okay? The two types of improper situations. Okay, so here's a couple of warm-up problems here. You ready? Here we go. So look at this integral, all right? And, oops, what's going on here? Yeah, Why is this thing not writing? Yes, it should be writing. Here we go. Integral of from -5 to 3 of 1 over x squared dx. Okay? Now you might say to yourself, well, that seems kind of easy. Why don't I just find an antiderivative and plug in the endpoints and take the difference? Well, the issue is the fundamental theorem of calculus demands that the thing you're integrating has to be continuous on the interval that we're thinking about. Does that make sense? And what's the issue here? There's a bad point. What's the problem point for this thing? 0, right? So the issue, so the problem is that the interval from -5 to 3, are you familiar with that notation? That little bracket notation for the interval? That interval contains x equal to 0, which is bad. Okay? Okay. Well, what do we do? Well, at the very least, we can kind of try to zero in on 0. Yeah? We try to hone our attention on 0 and break the thing up there and think about how we might deal with this. Does that make sense? Okay? So what we can do is we can say, well, this is equal to the integral. Okay, so you guys know, if I have an integral, I can always kind of pick an intermediate point and break it up into a couple of parts. Does that make sense? So where do you think I ought to break this thing up? What's the thing that is an issue for me here? 0, obviously. So there's going to be one chunk I'm going to look at, which is -5 to 0 of 1 over x squared dx. And there's another chunk I'm going to look at, which is where? 0 to 3 of 1 over x squared dx. Now, that's better. I've at least honed in on the problem, okay? And it's not like smack in the middle of the interval. It's at least on the end, right? You guys see what, before 0 was literally right in the middle of the situation, and now I've at least stuck it on the ends of 2 intervals, yes? But still, 0 is there. Do you know what I'm saying? 0 is still there, and that's still a problem. So what you do is you try to move a little bit away from 0, okay? You try to move just a little bit away from 0. Does that make sense? Okay? So watch this. The way you do that is by doing this. You say this is equal to the limit as, I need to use a couple of variables here. I'll say b, this is the letter b, it's not a 6, okay? As b goes to 0, and look, the problem is on the interval from -5 to 0 is, I don't want to go to the right of 0 because that will kind of put it in the middle of the interval again. So I want to go to 0 from which side? The left. So b goes to 0 from the left of the integral from -5 to b 1 over x squared dx. Okay? What that does is now this interval is actually good. Okay, so this interval, so this guy right here is now, we've gone from a bad situation to a good situation. Yes? B is to the left of 0, and I'm letting B get closer and closer to 0 from, oops, yes, thank you. What should that say? You guys are more on top of it than I am. B from the left. Okay? You guys understand? Now that's a good situation. I have kind of moved away slightly from the problem point, and yet at the same time, I'm going to let the limit go there. Does that make sense? I'm going to let the endpoint approach that bad point. Okay? And what am I going to do with the second guy? Okay, oops. What am I going to do with the second guy? Limit as what? A, okay, I have to use a different variable, okay? The limit as A goes to 0 from the right. This time it really is from the right. Integral from where to where? A to 3, 1 over x squared dx. And once again, this guy right here is now good. And what I mean by good is that I can actually apply the fundamental theorem of calculus now, yes? This thing is well behaved on any interval where I stay away from 0 a little bit, yes? Be it on the right side or the left side. So I can flat out apply the fundamental theorem of calculus now, yeah? Okay. You guys with it so far? So what are we going to have to do now? Yeah. So here, let me erase some junk here. Oops, I just erased the whole stinking thing. Can you believe that? Okay, so let me rewrite it. The integral from -5 to 3, 1 over x squared dx is equal to the limit as b goes to 0 from the left, integral from -5 to 0. Oops. Yes. -5 to b, 1 over x squared dx, plus the limit as a goes to 0 from the right, the integral of 1 over x squared dx. And this time I'm going from where? A to 3. And now we can use the FTC, the fundamental theorem of calculus. FTC applies. I still have to carry through the limits. I have to be very careful about what I'm doing here, okay? To communicate with my own self what it is that I'm actually doing here, okay? Okay, so this is going to be the limit as b goes to 0 from the left. What is the antiderivative of, okay, what is the antiderivative of 1 over x squared? How should I think of this? X to the -2, right? I should think of that as x to the -2, so that when I compute the antiderivative, it's negative x to the -1. So it's -1 over x, okay? So watch this. This is going to be -1 over x evaluated between, oops, oh my goodness. What is going on here, okay? Let me erase this. -1 over x evaluated between -5 and b. And I have to take that limit. It's the limit as b goes to 0 from the left of that junk. And what's the second thing right here? Limit a goes to 0 from the right of -1 over x evaluated between a and 3, okay? Okay? And now I have to actually plug in what these things are. So so the limit as b goes to 0 from the left, I'm going to plug junk in here. So it's -1 over b, -1 over b, minus negative, which is what? Plus, okay, that's sort of interesting. Plus what? Okay, minus, hang on a second. It's minus, minus, minus. Do you know what I'm saying? Because it's minus negative, and then I plug in -5. So overall, what do I end up with? -1/5. Okay? Interesting. Plus what? Limit as a goes to 0 from the right of -1/3 minus negative, which is plus 1 over a. Okay, and let's think about what happens with this together. Okay? So what about the first thing? What about the first thing? What does that go to? What's 1 over 0 minus what is that going to go to? Look, I'll just write this stuff in here. I told you last time that I'm fine with you doing this. I have a -1 over 0 minus, and it's okay to write that so you can think about what's happening here. And then I have a -1/5. Okay, and what's this going to be? Plus, okay, or actually here, let me write -1/3, -1/3, and what's this last thing going to be? Plus what? 1 over 0 plus. Okay. -1 over 0 minus means -1 over a teensy negative number. Yeah? Teensy negative number means something really, really close to 0, actually, and negative. What's that going to be? What's that going to be like? Yeah. This thing right here is going to be positive infinity. Do you know what I'm saying? And by the way, at that point, you're done. Once you have one thing that's like basically infinity, you're done. What you do is you say that this integral right here, okay, there's a word for it. You say that this thing diverges. This thing diverges. I don't even have to look at the other stuff. You might say to yourself, well, wait a minute, why couldn't a positive infinity cancel a negative infinity? No, 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 no. We don't play that game, right? We don't like think about some like positive infinity and negative infinity canceling each other out. If you have any part of the integral sort of like traipsing off to infinity, you're done. Does that make sense? So we are done at this point. This thing diverges because of this. But I mean, you can think about other stuff as well. What about the 1 over 0 plus? What does that also go to? That goes to positive infinity also, right? So look, I mean, if you were to actually say what the value of this thing is, you would say that it is infinity, yeah? You would say, well, this thing is actually, apparently has like infinite area. But even if one of the infinities was negative and the other one was positive, what would you still say? You wouldn't say infinity, you would just say diverges. Okay? But in this case, you could actually say that this thing, you could say with confidence that it diverges to plus infinity. Does that make sense? Now, before I take a question here, I at least wanted to show you something. Okay? I wanted to show you the following. Well, okay, yes, I'll take questions. So please ask questions before, because I want to look at the graph of this thing just so you can see why we're saying this thing diverges to positive infinity. Yeah, Jerry. I think I want you, I mean, look, I'm only asking you to remember 2 words here, either diverges or converges. Like eventually we'll talk about an integral converging. I do want you to use that language, and you'll know why once we get into chapter 9. That's all you're going to be saying over and over and over again. So you say, you have this improper integral. I want you to get used to saying this thing diverges to plus infinity, or it, converges to a 5th or something like that. If you have an improper integral, I want you to use the terms converge and diverge, okay? And we'll definitely be doing that. Yeah, Benjamin. Yes. Yeah, but you actually should be able to do that by hand anyways. Do you know what 1 over x squared looks like? Looks like this. I mean, look, I can even draw the graph over here. Yeah, so 1 over x squared. So I mean, look, it looks like this. Here's -1/5, right? Or -5. Here's 3. It's going to look like this. It's going to go choop, and choop like that. Yeah. So is it all that surprising to you that like how much area is there underneath this thing? I mean, look, it looks like a lot. You know what I'm saying? Yeah.
So like it doesn't matter like if you were to evaluate it, you go infinity plus infinity minus 8, like that's not.
Yeah, but subtracting off 8, I mean, who cares, right? Yeah. Yeah, that's not going to affect that. Now, here's the thing. There are times where you'll have graphs that look like this, where you actually will get a finite answer, and that's kind of the mystery of all this. Okay, but at least here you can see, oh, I see that there's the potential for this area to accumulate to infinity. Does that make sense? But again, if there is any part of the integral that goes to like an infinite value, like infinity or minus infinity, I better never, and look, I'm saying this right now, I better never see any of you trying to like cancel infinity. Does that make sense? Better never happen, okay? Don't do it. The other thing that can happen, by the way, is you can have sort of a wave, like a gaining of area and then a losing of area, and then a gaining of area and then a losing of area, and then a gaining of area and then a losing of area. How many times am I going to say this? It could just go on forever, and you never actually get close to any number. Does that make sense? When we say that an integral converges, it means that when you take the limit, it gets close to a number. And infinity doesn't count as a number, right? So infinity is like some other, mystical thing, yeah? But in this case, you would just say it diverges to infinity, okay? Yes, Andrew. No. Well, in this case, yes, but not in every case. Like, remember the wave situation I just talked about? So what's happening there? I'm losing it, but it's like you're never getting close to any particular number. Does that make sense? So that's another way that you can diverge as an integral. Diverge, look, you guys, diverge, that's like a word that we use in English language, don't we? I mean, it feels like diverge feels like we're not going to any specific place. Does that make sense? Okay, and even if it goes off to infinity, you're still not going to any specific place. You just are ballooning area forever, yeah? But when we say converge, what are we saying? You're going to a specific place, right? So the area is accumulating to a specific number, okay? So we use the word diverge here, and don't worry, we're gonna come back and talk about converge as well. But those are the two notions that we're trying to comprehend here in this context. Okay? Yes.
So you still have to find the first infinity, we can stop, but is there ever a scenario where we'll get infinity minus infinity, which is indeterminate? Can that like not happen?
So here's the thing, I can actually cook up stupid situations, like I could say, well, the integral of like x minus x or something like that. Like there are stupid situations like that, but technically, even if I do something like that, it still should diverge, because if I think about the integral of x itself from like 0 to infinity, I mean, that by itself is not going anywhere. It's just accumulating area forever. Does that make sense? Okay, so I still should say that diverges. But yeah, I don't think there's any real situation where I would be concerned about infinities canceling or something like that. The minute you have some kind of part of the integral that's infinite, boom, diverge. Okay? If you have a situation where the thing is just oscillating area, like gaining and then losing, gaining and losing, gaining and losing, but never getting close to any number overall, diverge. Okay? But if the limit ends up going somewhere, converge. Yes, Daniel.
So if we took a definite integral of a hyperbola, will it always be divergent?
No. No. There are situations where it will converge, yes. We'll see some of those too. Yeah. Yeah, those are good questions. Other questions? Any other questions? Okay, we'll definitely see situations like that, Daniel. Okay, so yeah, this picture, I mean, at least it looks like it's possible that we could be accumulating an infinite amount of area, yes? But weirdly enough, it turns out sometimes it actually still is finite, even though it looks like, you know, it kind of goes on forever, which is weird. Okay. Okay, other questions? So I at least wanted to, here, let me erase this. Okay. Let's see. I want to go on the old internet. I mean, you can always just graph things. So for instance, you know, I say y equal to, what was it, 1 over x squared or something? And I think if you say -5 less than or equal to x less than or equal to 3, does it know that? Or maybe, I'm trying to remember. How do you do that in Desmos? How do you give a range? I always know how to.
You need to like put it in separate brackets. The curly braces, I think, is how you do it.
Like this? Doesn't like that either.
Maybe try getting rid of the comma.
Oh, there we go. Okay. I always forget how to do that and have to re-remember. So do you see that? There's the picture right there. You can kind of see why the area would have the potential for ballooning to infinity. Does that make sense? Okay. All right. Back to the task at hand. Okay. So for improper integrals, in the fundamental theorem of calculus, f, the function that you're applying the fundamental theorem of calculus to, needs to be continuous on a closed interval. That's why, what did we do? 0 was still an endpoint, yes? That's why we moved away from those bad points. We first kind of isolated the bad point, and then we moved away from it so that we could apply the fundamental theorem of calculus, yes? And then we flat out took limits after that, okay? Okay, let's do another example here, okay? Oh, wait, so here's the two types of improper integrals. One or both of the limits are infinite, like one could be, you know, negative infinity, the other could be infinity, or there's an infinite discontinuity in the interval. Which case did we just find ourselves in? Infinite discontinuity. 0 was smack in the middle of the thing. I didn't have an endpoint that was like infinite. I just had a point where the function was bad. Yeah? Okay? So this is just kind of a rundown of what we do. If f is continuous on a to infinity, then what do I do if I have an integral from a to infinity of f of x dx? Okay, what do I do if I have an infinite endpoint? Well, I replace that in infinity with like b. Does that make sense? And I take the limit as that thing goes to infinity, and then I do the integral on that interval, and then I take the limit as b goes to infinity. Similarly, if I have like negative infinity as one of my endpoints, I take the limit as a goes to a negative infinity of the integral from a to b. Yes? This kind of this strategy making sense, what we're trying to do here? Okay. What about it? What if I'm on the interval from minus infinity to infinity? Then what am I going to do? Well, what you do is you just, okay, the first thing you do is you break it up, because what you want to do is divorce the limit going to minus infinity from the one going to positive infinity. So you break the thing up. Usually I like to choose c equal to 0, okay? You just have to pick something between minus infinity and infinity. Look, you might choose something different like 7, I don't know, but 0 is a good one to choose, right? And you just simply break the thing up, and look what it says. If the limit's on the right, or in part 3, one of the integrals on the right do not exist or are infinite, okay, we say the improper integral diverges. If you get a finite number oh man, it's kind of off the bottom of the screen here, but it says, if you get a finite number, the integral converges, okay? The integral converges in that case, okay? Let me escape out of here so you can see this. If you get a finite answer, the proper integral converges. Do you see that? So look, you break the thing up. If either of those things is infinite or doesn't exist, like it just oscillates around, what do you say immediately? Diverge. But if both of those limits exist and are finite, you say the integral converges. This is critical. What's that? Whatever it is. Yes, whatever the number happens to be. And we'll see examples of that. Yes, yes, yes. Okay. So once again, that number 4 thing right there is important. This is kind of the crux of the matter. If the limit on the right, okay, that limit on either part 1 or part 2, or in part 3, even one of the integrals in that sum, which I will require taking a limit. If one of the integrals on the right do not exist or are infinite, we say the improper integral diverges. Okay? If anything, okay, look, I'm saying this over and over again because I have seen the mathematical landscape littered with calculus corpses on this issue right here. Okay? I am telling you, I wish this were not true, but someone in this room will cancel an infinity at one point and say that the integral converges. Does that make sense? If any part of the integral, after you've kind of broken it up and taken limits, if any part of the integral goes off to infinity or the limit doesn't exist, any part of it, what do you say immediately? Diverges. It maybe diverge to infinity, but maybe it just diverges, like the thing does this, right? Or maybe it diverges to minus infinity, okay? But converge means that the limits exist, or all the limits in question exist and are finite. Yes. I mean, not unless you're asked for it. I mean, maybe if, it would be very specific in the instructions. It would say, if the integral diverges, either say that it just doesn't exist, or it diverges to plus or minus infinity. Say which situation you find yourself in. The does not exist one is like, you keep gaining and losing and gaining and losing, and you don't ever really get close to something. Yeah.
How would you get a finite answer
If one of the integral, the limits of integration are infinity? Yes. So we'll see an example of that here pretty quick. Okay. All right, other questions? Okay, so let's do an example like what Maria was just saying. Okay. Okay. So how about this? How about the integral? Okay, so watch this. Watch this. What about the integral from 1 to infinity? I mean, we're obsessed with 1 over x squared right now, okay? So what's the first step? Equals what? The limit as what? Let's let b go to where? Infinity. The integral from 1 to b of 1 over x squared dx. Okay, and what's this? This is going to be the limit as b goes to infinity. Of what? What is the antiderivative of 1 over x squared? We just did this, didn't we? Negative 1 over x evaluated between 1 and b. Okay, so this is going to be the limit as b goes to infinity of what? Negative 1 over b minus negative, which is plus 1. Interesting. What happens as b goes to infinity with that negative 1 over b thing? That goes to 0. So what is this overall? What does this go to? 1. The limit exists and is finite in this case. So what do you say about this integral? Yeah, the integral, right? So the integral converges to 1. Converges to 1. Okay? You could literally think of 1 as the value of that integral. Okay? Now here's the thing. I want to start really addressing something that that you may not be aware of right now. That is going to become a problem. When you are referring to these integrals, you need to treat them with the proper respect that they deserve. And that means you do not refer to them with pronouns. You don't say it. Okay? The issue is when you say it, look, I'm sort of joking, but I'm also serious. When you say it, there are too many things that you could be referring to. I don't know what that means. It could be the limit. It could be the endpoint. It could be the integral. So you need to treat the integral with the proper respect and refer to it by name. You say, like, so how did I refer to it here? Integral. I actually said what I was referring to. I didn't say, so it converges to 1. Notice that I did not say the word it, okay? So please refer to the thing that you mean, and this is going to start to become a massive issue in chapter 9. Treat, use the terms that refer to the thing that you mean. Don't say it. Don't say that, so the thing converges or something. Just respect the integral, okay? Just call it by name. Say that integral, right? Or give it a name. Call it Joe. And say Joe converges or something, right? But please, don't say it, okay? And I will have that discussion with you at some point in the future as well. Okay, because that will clearly start to become a problem eventually. Okay, so that's interesting, huh? Any questions on that? So we've seen an example where we have divergence. We've seen an example where we have convergence. We've seen an example of an infinite discontinuity. We've seen an example of an infinite endpoint, right? This time we had an infinite endpoint that we had to deal with. Okay. And let's look at the picture here in this case. Okay, so going back to Desmos here. Okay, there was this one. I'm going to turn that one off and I'll say, okay, so now I want y equal to 1 over x squared. And where was I this time? Well, it's kind of weird, but it was 1 less than or equal to x less than or equal to, man, does it even know what infinity, oops. Infinity. Oh man, check that out, right? Okay. Less than or equal to, I can't believe it didn't rebuke me for that, right? So less than infinity, yeah? So here's what this thing looks like. Oops, I zoomed in way too much. Okay. So apparently this right here races towards, like the asymptote of the x-axis here, it races towards that fast enough that it prevents the overall area from accumulating to infinity. That's sort of weird, isn't it? Like the overall, okay, so that area right there under that curve is prevented from accumulating to infinity, okay? It looks like it's like it races toward the x-axis fast enough so that it kind of caps it off. And there are actually some geometric argument or some geometric ways that we can actually see why that's happening here. But that's sort of weird, right? Yeah. No, it's not. It's 1. So I mean, there is a way that we could actually see in this case, and I'll show you some pictures like maybe tomorrow. There's a way that you can see that all of that area fits inside of a box that's 1 by 1. There's a way that you can actually see that. Okay? Yeah, there's a way that you can actually see that. It's sort of weird, but it's true. Okay? All right. Yes, Daniel.
So why would we refer to this as, so this actually equals one, it's not like the limit.
Yeah, I mean, you could actually, yeah, you could say it converges to one, or in this case, you could actually say it equals one. Yeah, yeah.
Well, like limits, like you're not actually getting to that number. So if you say like,
He's saying it's just an approximation.
yeah, in other words, a limit is an approximation. So is there a situation where the limit would equal something and it wouldn't actually equal that number? So you said like we can take all this area and put it in a 1-by-1 box. But is there a situation where we would get an area, like a number, a limit approaches a number, but it doesn't approach, but it doesn't actually fit in that box?
No, no. It would, you know, I can't imagine a situation like that. It all behaves like if the limit equals a number, then, I mean, every situation I can think of that you can actually describe geometrically, it makes sense in terms of it fitting inside of a proper box of area, whatever it is that you're looking at. Yeah, yeah. So nothing strange like that happens. Now, when we get to series, which are infinite sums, we'll have some weird situations. Okay. So yeah, so just stay tuned on that one. Okay. So let me see here. I think I actually have just a second here. Yeah. I'm gonna actually post this on the website, but here's the thing. Here's like a situation where, look at this. I'm sort of showing you how it is that you can add up an infinite number of things and have it still sort of fit inside of a square. Okay? So look at this. The square itself is like so you see this square on the right? It's like a 1-by-1 box. Do you see that? And look, what I'm showing you is this is a way that you could have an infinite number of things adding up to something that's finite. Okay? So what you start with here is like a 1/2-by-1/2 box. Okay, do you see the 1/2-by-1/2 box sitting there? And then what you do is you have a 1/2, or actually a 4th-by-1/4 box, and then a 1/8-by-1/8 box. Do you notice what's happening here on the bottom edge? It's like half the previous thing. Does that make sense? Okay. And it turns out that if you add all of these things together, that you end up with something that actually stays inside of that 1-by-1 box. Sort of bizarre. Okay. So yeah, go think about that at Chuck's for a little bit, but we'll talk a lot more about this in the future. Okay. Have you ever heard of something called oh man, I'm going to get there's like the tortoise and the hare situation. So like, for instance, if the tortoise gets ahead of the hare, then the hare can never pass the tortoise, because at some point it's going to have to pass the halfway point, and then the half of the halfway point, and then the half of the halfway point. There's an infinite number of points that it would have to pass the hare. But then, so we say, how does it pass the hare at some point? Because it does. What is going on, right? And so that's kind of the sort of thing that we're talking about here. Even though there's like an infinite number of points that need to be passed along the way, it still happens, right? And it kind of, like the amount of distance between the hare and the tortoise is eventually evaporated, okay? So there's going to be some weird discussions in the future about adding up an infinite number of things and ending up with a finite amount, And we just saw that in this integral that we just did together. Okay? All right. Let's do maybe another example here. Okay, so what about this? So what about this? The integral of from 1 to infinity of 1 over x dx. And this one I'm going to let you kind of work on with people around you. Okay? So work on that with people around you. Integral from 1 to infinity of 1 over x dx. Work on that with people around you. Figure out what to do, and let's reconvene and see what you come up with. Okay. So what do we have going on here? How do you write this as a limit? Limit as b approaches infinity. 1 to b, 1 over x dx. What is the antiderivative of, right, so this is going to be natural log of x evaluated between 1 and b. So it's going to be the limit as b goes to infinity of logarithm of b minus logarithm of 1. What's logarithm of 1? 0, right? So this guy right here is 0. What about logarithm of b? What does that go to as b goes to infinity? What's the logarithm function go to as b goes to infinity? It goes to infinity, albeit pretty slowly, but it's still plus infinity. So what do we say here? So the integral diverges. And in this case, we could even say to what? To positive infinity, okay? Now the graph of 1 over x on 1 to infinity looks similar to the graph of 1 over x squared, okay? So for instance, so let me just, so any questions on that? I want to show you a picture here. Any questions on that? Right, so the graph, let's go over here to the graph. Look, what if I look at y equal to, that? This time I had 1 over x, right? From 1 less than or equal to x less than infinity, okay? Well, look at this. So look at the blue curve and the green curve. The green curve we already determined only accumulates an area of 1. Does that make sense? What do you notice about the blue curve though? It's quite a bit bigger, right? It's not going to it's not approaching the x-axis as quickly, and therefore it doesn't prevent the accumulation of area. It doesn't prevent the accumulation of area not having any ceiling. So that area actually blows up to infinity. Yeah. Yes, it's 1 over, right. Yes, it's 1 over x. Yes. So like a power bigger than 1, like 1 over x to the 1.01. Even that, if I integrated that from 1 to infinity, would be finite. But 1 over x to the first, that obviously, okay, we just showed that that diverges to infinity. If I went 1 over x to the 0.99, that's going to be even worse because it's going to go down even slower. Does that make sense? And it's going to accumulate area too fast. Okay. But the threshold is 1. So anything above 1 will converge. And anything below 1 will diverge. Okay. So that's interesting. And that, my friends, will actually be very important later on. Okay. Those are called, I won't get into it right now, but it has something to do with something called P series. You might have seen that at the top of that little paper I just showed you. Okay. Other questions? All right.
Are we starting 9 tomorrow?
No, we'll do a little bit more with this, but then yeah, then we'll be on to 9. Yeah, the start of 9.